Hi everyone, today we're going to talk about the properties of a rational function. What we're going to do is be graphing these and determining the different key features. So the first thing we're going to look at is determining the domain. And as we can recall back when we have this rational function, you get the domain by setting the denominator equal to 0, and then whatever that equals, that's what x cannot be, because if 0 is in the denominator, that makes your fraction undefined. So you don't want 0 in your denominator. So if we look at this 1 over x squared, if we take x squared and set it equal to 0, we get x equals 0. So x cannot equal 0 for this case. So let's go do a couple examples. So I'm just going to take the denominator, x plus 5, set it equal to 0, and say it can't equal it. Subtract 5 from both sides, and I get x cannot equal negative 5. You can leave it as x equals negative 5, but you can also write it in the notation x cannot equal negative 5. Next, we do the same thing. X squared minus 4 equals 0. Add 4. X squared equals 4. Square root both sides. You get x cannot equal negative 2 and positive 2. Remember, if you take the square root of something, you get the negative and positive version of it. Now let's do x squared plus 1 equals 0. Subtract 1. We get x squared equals negative 1. We're going to square root both sides. Whoops, we have a negative in our square root. So that means that we can't do that. So when we can't do that, our domain is all real numbers. Okay. Last one, x minus 1 equals 0. Add 1, x equals 1. So you're always setting that denominator equal to 0, and then whatever you solve for x, that's what your domain cannot equal, or at that x equals, nothing is happening at the graph at that place. Alright, so let's look at 1 over x squared, and we're going to look at what this graph looks like. From up above, we notice that the denominator cannot equal 0, the domain cannot equal 0. So x such that x cannot equal 0. Now let's look at the y-intercept. This is when you set the equation equal to 0 and solve for x. So 0 equals 1 over x squared. You would multiply each side by x squared and get 0 equals 1. That's not true. So that means there is no, so y-intercept, none. Okay, now we want to try and find the x-intercept. This is when you plug in 0 for x and then solve for the function. If we plug in 0, we just come back to how x cannot equal 0. So that means this function has no x-intercepts. Lastly, we're going to determine if this is an even, odd, or neither function. So let's try even. So that's when h negative x. So that would equal, plug in that negative, and that still equals 1 over x squared. So this is an even function. All right, now let's put all that together into a graph. So we have no y-intercept, so nothing's happening there. So I'm going to put a dotted line. And nothing's happening at that x-intercept. And then that graph looks like this. You can always make a t-chart and plug in values if you can't remember what the graph looks like. Otherwise, you can just remember that 1 over x squared looks like this. Now we're going to take that 1 over x squared and use some transformations. So the first thing I notice is that x minus 2. And if we remember, in the parentheses, it's the opposite in the x direction. So we are going to go 2 to the right. and then I have that plus 1. So that means I'm going to go 1 up. So from our original graph, I had a dotted line at 0. I'm now going to have it at 2 because I went 2 to the right. And then I had my other dotted line on the x-axis, and now I'm going to go 1 up. So my other dotted line happens here. And then I'm just going to go in and fill in those lines again. And then that's what this graph looks like with those transformations. Okay, next we're going to talk about the different asymptotes. So like those dotted lines that we were just drawing. So there's different scenarios for each one, and not all graph has both or any at all. So you really have to look at the rational function and determine which one it's going to have. So a horizontal asymptote is if the degree of the denominator is bigger than the numerator. The horizontal asymptote is at the x-axis of y equals 0. If the degree of the numerator is bigger than the denominator, there is no horizontal asymptote. And if the degrees are the same, the horizontal asymptote equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Vertical asymptotes, happens at the zeros of the denominator. So when we set the denominator equal to 0 and then solve for x, that's where our vertical asymptotes happen. Next is the oblique. These are like sideways, slanted. Another word they use for oblique is slanted. And this occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. And to find it, you divide the numerator by the denominator. And you can do this using synthetic division or long division. So let's go look at a couple examples to get some practice. The first thing we're doing is finding those vertical asymptotes. So we are going to set those denominators equal to 0 and solve. So x minus 1 equals 0, x equals 1. So that means we have a vertical asymptote at x equals 1. Next, we have the x squared minus 4 equals 0, x squared equals 4, x equals negative 2 and positive 2. So we're going to have two vertical asymptotes at x equals negative 2 and x equals 2. Next, we have the x squared plus 1 equals 0, x squared equals negative 1. Can't take that square root, so no vertical asymptotes. Okay, this last one we need to go ahead and factor that denominator to set it equal to 0. So we have x squared plus 4x minus 21 equals 0. We're going to go ahead and factor, so we need two numbers that multiply to negative 21 and add to 4. That is 7 and negative 3. So we have x plus 7, x minus 3 equals 0. Set both of those equal to 0, so x plus 7 equals 0, x minus 3 equals 0. We get x equals 3, and x equals negative 7. So we have vertical asymptotes at x equals negative 7 and x equals 3. Now we're going to go ahead and start looking at the horizontal asymptotes. So to look at the horizontal asymptote, we need to check out those degrees. And it looks like the degree in the numerator is less than the degree in the denominator. And if we go back and look at our rules, this says that the horizontal asymptote is going to happen at y equals 0. So we have a horizontal asymptote at y equals 0. Okay, now we're trying to determine between if this is a horizontal or oblique. And if we look at this, our numerator is 1 more than the denominator. So let's go look at our rules. This then is an oblique because our numerator is exactly 1 greater. So we're going to divide the numerator by the denominator. So we can take 3x to the 4th minus x squared, and we can use long division and divide it by that x cubed minus x squared plus 1. I'm going to go ahead and go back inside that square root or our division sign and add in those missing pieces like the 0x cubed, and then we have a minus x squared, but we don't have an x and we don't have a 0. I'm just going to add those in. Okay, so I know I'm going to need to multiply by 3x to get that 3x to the 4th, and then minus 3x cubed, and then plus 3x. We're going to go ahead and add these together. So we get negative 3x cubed, or we're going to subtract these. So I get negative 3x cubed minus x squared, and then plus 3x. Yep, add those together. Next, we are going to say, okay, what do I need to multiply? X cubed minus x squared plus 1 to get something close to this, and that would be 3. So we're going to say plus 3. And we're going to have 3x squared minus 3x cubed minus 3x squared plus 3. We're going to subtract that and get 2x squared minus 3x minus 3. So we have an oblique asymptote at y equals 3x plus 3. It is whatever you came up from the top up here. So y equals 3x plus 3 is the oblique asymptote. All right, let's look at this next one. We have the degree of the numerator and denominator are the same. So if we look at our rule, we take the coefficient of the numerator and divide it by the coefficient of the denominator. So our leading coefficient is 8 in the numerator, and the denominator is 4. So 8 divided by 4 equals 2. So we have a horizontal asymptote at y equals 2. Lastly, we have the numerator is bigger than the denominator. So let's go look at our rule. Numerator is bigger than the denominator. There is no horizontal asymptote. So no horizontal asymptote. If you have any questions,